and welcome class to the beginning of chapter 13 in Burge and Overby's 4th edition, Chemistry Atoms First. Chapter 13 is all about solution properties, which we call colligative properties. Very fancy word, and that is where we are going in this chapter. But before we talk about these properties, we need to make sure that we understand, in more technical senses, the construction of a solution. So that's going to be what we talk about today. Now, there are different types of solutions, and this we've introduced already the concept of in chapter 12 that solutions don't have to be aqueous. A solution, by general definition, is just a homogeneous mixture where you have some solute or a number of solutes, for example, salt, and these solutes are dissolved in some given solvent, for instance, water. And these are the most common solutions that we consider in general chemistry are aqueous solutions. But again, it doesn't have to be salt and water. It could be any number of phases, just so long as we have some lesser amount dissolved in a greater amount, creating a homogeneous mixture. The thing that all of these solutions also have in common is that they are stabilized by attractive intermolecular forces that can take a number of different forms. For instance, sodium chloride in water are stabilized by ion-dipole intermolecular forces, and any combination of solute and solvent can be analyzed to hypothesize what IMFs are causing this attractive solution or this stable solution in the first place. All right, as we've also discussed though, to reiterate, solutions can be in any phase. So we can have gaseous solutions like we have illustrated on the left. We can have liquid solutions, which we have illustrated in the center, or solid state solutions, which are illustrated on the right. So on the left, what we actually have is Cl2 in air. And because of the great abundance of air inside of this flask, and the lesser amount of the chlorine gas present inside of this flask, we would actually consider this to be a homogeneous mixture, therefore some type of gaseous solution. The liquid, it looks like we just have a variety of dyes dissolved in water. To me, it looks like blue dye number 1, red 40, and green 3. But because the dye is present in lesser amount comparatively to the water, we would consider the dye to be a solute and the water to be our solvent. And last but not least, it appears on the right as though we have some brass here, and brass is a combination of zinc and copper. All right, so the combination of solids, liquids, gases, in addition, can also give rise to some type of solution. For instance, salt is a solid. When we dissolve it in water, it breaks into ions. So there's definitely some like mixing and matching that we can also see that would lead to a homogeneous mixture. And again, the takeaway is we're going to have to have some attractive intermolecular forces in order to stabilize our solution. So what we're going to be focusing on in chapter 13 are aqueous solutions, but a lot of the same arguments that we can make about different phases and different phase solutions can be seen here as well. So an aqueous solution, as a reminder, is specifically a homogeneous mixture in which water is the solvent. It's not just that water is present, but specifically that water is the solvent. And so, as we've already stated, one hypothetical solution is salt, which we can see up here, sodium chloride inside of the spoon being sprinkled down into our good old H2O below. And just with the simple prompting of stirring, the water is able to attack and dissolve our sodium chloride crystals, which is what is being illustrated here on the right. Now we can see in the center of this illustration, it seems like there's still a chunk of sodium chloride crystal left, but it's definitely being slowly eaten away at by these water molecules, where we can see that the positive hydrogens in our water molecules are attracting the negative chloride, and similarly the negative oxygens in our water are attracting this positive sodium from the salt. And so starting from the outside, working their way in, these water molecules will pull the sodium chloride apart piece by piece, where the sodium chloride is also more stable in doing so thanks to the ion-dipole intermolecular forces present between these species. So we've talked about most of these things before. Going back to chapter 9, that's when we can trace when we first really started talking about aqueous solutions specifically. So let's introduce something new. We're going to look at the more expanded view of how water continues to stabilize these ions in solution, because it's not just enough to have one or two water molecules, but rather the water molecules are going to create very stable spheres of hydration around the ion. Now, these spheres of hydration are also synonymously known with spheres, the spheres of hydration are also synonymously known as spheres of solvation. And by technical definition, these are clusters of solvent molecules that surround an ion or molecule in solution. So whether it be the positive sodium, which we can see on the left, or the negative chloride on the right, what each of these things have in common is that they are stabilized by an immediate web of 6 water molecules. And this is not a coincidence. 6 seems to be the magic number with water. It is the most stable number of surrounding water molecules that we can have around a single ion in solution. But of course, these water molecules immediately surrounding the ions don't exist in a bubble. They exist in solution with even more water molecules. And so the waters that are forming these, as we can see here illustrated in green, ion dipole forces with our ion, there's another layer of water molecules surrounding the first, stabilizing them via hydrogen bonds. And there's another layer around the second, stabilizing those by hydrogen bonds. And so we're creating these spheres, these bubbles of very highly coordinated water molecules around our solute that will stabilize the solute and the solvent inside of solution. The presence of these spheres of hydration will become more important as we begin talking about solution-specific properties, and I will continue to use these terms throughout the semester. So spheres of hydration are very important, and they help us to understand exactly how aqueous solutions differ in property as opposed to the pure solvent, our water. Now, just because we put two things together, a solute and a solvent, doesn't mean that they will absolutely attract one another. There's definitely a balance of the intermolecular forces present inside of our solution, and there's only so much that the spheres of hydration can do for particular solute particles. For example, if a solute particle does not form stable electrostatic intermolecular forces because they're incapable of holding stable positives and negative charges, we would call these particular solute types hydrophobic. Hydrophobic literally translates to water-fearing. These are solutes that are destabilized by water's polar intermolecular forces. They would rather interact through other means, such as dispersion. Sodium chloride we would consider to be a hydrophilic or water-loving solute. These types of solutes are those that are stabilized by water's polar intermolecular forces because they are also able to form polar bonds to some degree. Now, these are the most extreme cases. Hydrophobic things like oil being mixed with water tend to result in pure heterogeneous mixtures. So we don't even have an aqueous solution when it comes to mixing hydrophobic things with water. And the hydrophilic things, like our NaCl, tend to result in homogeneous mixtures or solutions. Homogeneous mixtures. So in the first case, we get no solution because there's nothing dissolved in anything else. In the second case, we get yes solution. But there is a third option in the in-between of this extreme binary. We call these things water-tolerating solutes. For example, bromine, or Br2, which this is, I now realize, a typo. This should be written as Br2, which we can see illustrated here. These molecules are partially stabilized by water's intermolecular forces. They can be accommodating to the polar forces, but they're not super stabilized by them. So let's look at this picture on the right, and we can use our skills of inference to determine what's happening here. So bromine is one of the two naturally occurring liquid elements on the periodic table. The other is mercury. Even though it exists as a liquid, we can see that it is very volatile. There is a lot of this brown gas existing above the liquid. Makes sense, right? As we've already talked about, liquids will have some measure of vapor pressure above the surface of the liquid. It just happens with very volatile liquids like bromine, we're going to have an abundance of gas, whereas very non-volatile liquids like water, we will have not a lot of gas and therefore a very low vapor pressure that naturally exists above the liquid. All right, if we mix, though, liquid bromine with liquid water, what we can see is two layers that form. The first is brown water, which we can conclude is the result of water mixing with a certain amount of bromine, but then we can see that there is another layer that still exists down below, where there is a lot of excess bromine that is not able to be stabilized by water. And so here's where we acknowledge the balance of the intermolecular forces. Up above, we do see that there is a mixture that is forming. We do have a solution, and so we can rationalize water's ability to stabilize some of the bromine through what we call induced dipole intermolecular forces, where bromine in its covalent form naturally does not have a dipole moment. However, it is a pretty small molecule, and due to the large elemental sizes of bromine is fairly polarizable. The partially negative side of our water is going to be able to push the electrons from one side of the bromine to the other, leaving us with a partially positive charge on one end, a temporary partially negative charge on the other end, and this would be able to then attract another water molecule, specifically through the hydrogens, which are partially positive. So we can see that there are going to be some stabilizing interactions here, but it's going to require bromine to behave and to consistently push its electrons from one side to another. Because that is not in bromine's nature to have a charge, it's going to fight that, and ultimately not all of the bromine is going to be able to dissolve inside of the water. Some of the bromine is going to say, you know what, no, I'd rather interact with other bromines without charges through the process of dispersion, which we've talked about already, dispersion being a weak covalent-like kind of bond where electrons are able to rapidly exchange from one molecule to another. This is a much more stable means for bromine to interact with other molecules, and in fact it can interact that way with water, but as we already know, water is the most stable when it forms polar interactions, things like dipole-dipole bonds or ion-dipole bonds. So due to the discrepancy with how these two molecules would prefer to interact with other molecules, yes, some of the bromines can be coaxed into forming a mixture with the water, like we can see here in the upper section of this test tube. However, the solution is going to become rapidly saturated. In other words, there will not be room for any extra bromine because all of these water molecules are going to have to coordinate so much with the bromine that there's not going to be space for all of the bromine. There are going to be some bromines that get away and form this separate layer, not in the solution, down below. There are other molecules like bromine that we would call water tolerating. So long as they are small molecules, they can be coaxed into bonding with water through some type of polar bond or some type of charged bond. But the larger the nonpolar molecule, the more and more hydrophobic it will become. All right, so we've been talking about creating solutions and physically what it means. So we need to have some stable intermolecular forces. These stable intermolecular forces must result in a homogeneous mixture between our solute and our solvent. And of course, there's going to have to be some type of energy change or energy exchange in the process. Since we normally are taking some type of solute that is in solid form and breaking it apart, of course there's going to have to be an exchange of energy somewhere. This energy that is necessary to make a solution is known as the enthalpy of solution, or delta H sub solution, SOLN for solution. This is specifically the heat absorbed or released. It can go in either direction, all depending on the material, as a solute dissolves in the solvent and since we're working with aqueous solutions, again, we're going to consider the solvent to be H2O, per every 1 mole of solid, aka solute. Now we can make sense of the enthalpy of solution and all of the sub-pieces that go into it by observing the diagram on the right. So our enthalpy of solution is going to be the sum of 3 different lesser enthalpies, each one of which is labeled here in the diagram somewhere. The first thing that we need to physically consider is the solvent itself. Now the solvent may be accommodating to the solute, right? Our water may want to dissolve sodium chloride, but it's still going to cause a disturbance in the naturally occurring flow, the mojo, the zen of the solvent itself. We're going to have to make space for the solute. And in doing so, we're going to have to spread these molecules apart in order to adjust and to accommodate. The energy necessary to separate our solvent is known as delta H1, at least in the diagram that it is labeled in here. The process of spreading out our solvent is going to weaken the intermolecular forces holding the liquid together in the first place. All right, next we turn our attention to the solute crystal. This is going to be, for instance, again, like our sodium chloride or our bromine or anything that's going to be able to dissolve inside of the solvent, anything that's water tolerating or hydrophilic enough. Similarly, though, we're going to have to spread out, again, that solute. We're going to have to make sure that we're breaking it apart piece by piece. Physically, the water is able to do this 1 ion or 1 molecule at a time, but energetically we are going to have to observe from initial conditions to final conditions, and so there will be a corresponding enthalpy required to spread out the solute. For something like sodium chloride, that is actually an ionic crystal, this is going to end up being something like the lattice energy of the crystal, how much energy is necessary to actually break something apart. It will not literally be equal to the lattice energy because of how lattice energy is technically defined, but it's something like that, right? We're looking at the energy of the bonds holding the solute crystal together, and we're going to have to break those to spread them apart inside of the solvent. All right, so energetically speaking, this is delta H1 and delta H2. We need to spread out the solvent and spread out the solute in order to make room for them to mix together. Once we put them together, this is going to be equal to delta H3, creating the solution. So delta H1 corresponds to, again, breaking the intermolecular forces between the solvent. Delta H2 corresponds to breaking our quote-unquote lattice energy. Delta H3 is making the new intermolecular forces. We are now creating bonds, and these bonds will stabilize the solute and the solvent together. So when we make bonds, we know that this is an exothermic process. So delta H1 and delta H2 are endothermic. We need to put energy in to break things apart. This is why in our equation, both of these things are positive. It's because they're endothermic processes. Our delta H3, the making of new intermolecular forces, we know is an exothermic process. Exothermic, because we release energy when making these bonds, hence why this delta H3 here is negative. So each of these 3 individual pieces, delta H1, delta H2, and delta H3, we can look up in some type of table or calculate computationally, and when we put these 3 pieces together, we would find an enthalpy of solution. It can be difficult, though, to find delta H1, delta H2, and delta H3 experimentally, which is where it's useful just to directly observe our delta H of solution, which can actually be found in the lab using calorimetry! Exclamation point. So this calorimetric method that we have already discussed back in chapter 10 can be useful for directly finding enthalpies of solution. So for example, our enthalpy of solution for potassium nitrate, which can also be found in lab directly, is equal to 34.5 kilojoules per every mole. Now this process, we can see, because of the positive enthalpy of solution, is endothermic. So as it turns out, the breaking of the bonds between the solvent and the solute, our delta H1 and delta H2, require more energy than the making of our intermolecular forces releases. And this is going to be true for a great number of enthalpies of solution. Even though these processes are spontaneous, which we'll talk more in chapter 14 about what it means to be spontaneous, but suffice to say, if you take potassium nitrate, which we know from our discussion in chapter 9 is a soluble solid, and dissolve it in water, it will dissolve. It just so happens that this is a spontaneous endothermic reaction. And we know that these exist as well. Just because a reaction requires more energy than what it gives off doesn't mean that it's not going to happen. If, however, an enthalpy of solution is negative, corresponding to an exothermic reaction, what that means is that more energy was released in the forming of the solution as being compared to the breaking of the bonds between the solvent and the solute. So there's definitely this balance here. It's not impossible to have exothermic enthalpies of solution. It's just less common. The discussion of potassium nitrate and solubility, though, brings us full circle from chapter 9 to rediscuss what it means to be soluble. So here in chapter 13, we're going to be focusing on the mostly soluble category from back in chapter 9, because we did acknowledge a bit of the gray zone between the soluble and the insoluble, things that can and cannot dissolve respectively. We are not going to turn our attention back to the mostly insoluble things until chapter 17. Mostly insoluble here. And the reason why is there are a couple of more, let's say, technical and difficult definitions and concepts that we need to talk about before we can turn our attention back to the mostly insoluble. So let's just focus on what's in front of us, the mostly soluble compounds, as well as discuss again what it means to be soluble. Solubility, by definition, is the quantifiable amount of soluble solute that will dissolve inside of any given quantity of solution at some specific temperature. And we measure solubility in the units of grams per liter. Specifically, how many grams can we fit inside of a liter of solution? Now, there are two definitions that we are going to introduce. At least first, immediately. The first is what is known as the unsaturated solution, which is illustrated here on the left. The second is a saturated solution, which we can see here on the right. So let's technically define these terms and then come back to these pictures to get a better idea for what they're illustrating. All right, so there are different degrees to which we can saturate a solution. By technical definition, an unsaturated solution is one that contains less solute than the solvent has the capacity to dissolve. In other words, you could always dissolve more of that given solute, and again, at some given temperature. And we'll talk about the temperature dependence of solubility in a hot second, but first we're just going to assume we're at a constant temperature. What does unsaturation versus saturation mean? Well, unsaturated means that you're not saturated yet. Again, you could always fit more solute inside of the solution. There is still space between solvent molecules where more stuff could fit. And you can fit stuff in solution up until you hit the saturation limit. A saturated solution is one that contains the maximum amount of solute that can possibly be dissolved. No more solute can fit. And there is always going to be a point where you will reach the saturation limit. With some solutions, it comes earlier, some solutions, it comes much later. It all depends on how soluble your material is. For instance, salt in water, like sodium chloride, literally is super soluble, and you can fit a ton of it in solution before the excess will begin to gather at the bottom of the container. So if we go back to our previous illustration, that's exactly what is being illustrated here. In your unsaturated solution, there is still more space for solute. We can still see that there's like an open space right here between our water molecules. There's open space down here for the water, or like in between the water molecules, there's open space up here. And so it looks like if we were to take all of our solute particles, which are these blue things here, the solute, like physically we would sprinkle this in solution and see it all dissolve, we'd see it all disappear. So the solution would become clear, it'd be a nice homogeneous mixture, and this is because we still have not reached the saturated point yet. Now on the right-hand side, we are observing a saturated solution. No more solute can fit! Exclamation point. Now if we are just at the saturation limit, we would not see any excess solute being present inside the container. It would still look like a homogeneous mixture. But as soon as we add one extra solute particle, well, there's nowhere else for it to fit. It seems like all of the spaces have been taken between all of our solvent particles, which are technically here forming spheres of hydration. I just didn't illustrate that for ease of clarity. But each of these solute particles is surrounded by our spheres of hydration, and no more water molecules are free to form any additional spheres of hydration. So because the solute has nowhere to go, it's just going to start piling at the bottom of the bottom of our container. We are going to start forming a heterogeneous mixture now. Heterogeneous, because there's nowhere else for this solute to fit. We have actually already today seen a great example of a saturated solution physically. If we go back here, and I'll clean this up again just so it's less intimidating, our picture on the right-hand side is an illustration of a saturated solution. Right, all of the solution up on top, all of our solvent is currently occupied with as much bromine as can possibly fit. And so because there's no space for the extra bromine, because it's water tolerating at best, the excess has now pooled at the bottom, creating a homogeneous layer up on top, but a heterogeneous mixture overall. Another great example of a saturated solution is that which is made or used to make rock candy. So inside of each of these solutions, the red, the green, the yellow, and the blue, we have saturated solutions of sugar water. Now, just because there is more solute than what can possibly fit inside of the solution, it doesn't mean that it will all always pool at the bottom. It's just going to end up collecting on what is the most convenient place for it to gather. And so we have, in making rock candy, taken advantage of the coarse nature of the wood, which gives the sugar crystals a place to go, to adhere to. So if you ever want to make rock candy at home, all you need to do is dissolve a bunch of sugar inside of water, and you can look online to find exactly how much sugar you should dissolve in the water, and then tie some sticks up on the top, you can see hang down in the solution down below, and just let it sit. As the water inside of this solution begins to evaporate away due to vapor pressure, which we've talked about already, there's going to be less solvent available for your solute, and with nowhere else to go, the solute is going to start pooling and collecting on this stick, growing out in these beautiful dyed crystals, assuming that you add food dye as well, and as an end result will leave you with some delicious rock candy. Again though, turning our attention back full circle to our definitions for unsaturated versus saturated solutions, these rock candy solutions are saturated. And the reason why they are saturated is because the solution itself is already contains the maximum amount of solute that it can possibly contain. The rest that it cannot fit is collecting on the stick instead. There is a third definition that we must discuss though, and this is known as the supersaturated solution. A supersaturated solution is a solution that contains more solute than what the solvent actually has the capacity to dissolve at a given temperature. And you're like, how can that even physically happen if there's no space for the solute? Where does it go? Well, the answer there is we have to acknowledge that any aqueous solution contains a tiny amount of solvent or solute compared to the massive amount of solvent that is inside of the container. And the saturation limits of these solutions tend to be found on average. And there are always ways experimentally, physically, or environmentally that we can get around what we commonly see is the saturation limit. For instance, one really common way to make a supersaturated solution is to take a solution, add a little bit of extra solute to it, and jack up the temperature. Now, as it turns out, we can increase the solubility of a solution by increasing the temperature. So the extra solute will dissolve at a higher temperature. And once it dissolves at this higher temperature, what you do is let the temperature slowly come down of its own accord. Don't add ice, don't shock the solution. And as the temperature slowly cools down, the water molecules will have no choice but to allow the solute to remain dissolved, even though the solution becomes slightly unstable in the process. Now, this can have two pretty great results. The first is an excellent demonstration which we commonly perform in general chemistry classes by taking sodium acetate, which readily will be able to form supersaturated solutions. So you increase the temperature, right? Bring your water up to boiling, add some extra solute, and let the temperature slowly cool down. And the demonstration itself is that you take an extra granule of sodium acetate and throw it into the solution, which will cause the extra solute to rapidly fall out or precipitate out of solution in these beautiful patterns like you can see here. Another very common supersaturated solution is that of Texas iced tea or Southern sweet tea. Southern sweet tea is made by boiling water and adding an abundance of extra sugar, which when slowly cooled back down will not crash out of solution. Instead, we end up with this delicious drink that has way more extra sugar than what the solvent or the water is naturally able to hold. So these things, these Texas iced teas or these sweet teas, we are able to drink like pretty freely. We can even cool it down with an extra amount of ice for an extra sweetness on top of the already supersaturated solution. All right, so that transitions us into the last thing that we have to talk about today, which is the temperature dependence of the solubility of solutions. So supersaturated solutions are not the only solutions impacted by an increase of temperature. In fact, the solubility of solids in solution will always increase with increasing temperature, with very, very rare exception. I guess I shouldn't say always if there's a rare exception. So yes, generally, I'll put it that way, 99% of the time, your solids are going to increase in solubility with increasing temperature. And that is exactly what this graph down below is illustrating. On the y-axis, we have solubility in grams per 100 milliliters of water. And on the x-axis, we have temperature. And for nearly every single one of these materials, every single one of these solids, whether it be glucose, sodium nitrate, copper sulfate, sodium chloride, we can see that there is a positive correlation here. So the solubility of your solution goes up with increasing temperature. The only material that has a negative association on this graph is cesium sulfate, which is a mostly insoluble compound in the first place. Now we can see most of these solids have a linear relationship or a mostly linear relationship between solubility and temperature. One material we can see here that has an exponential or a powered based relationship is sodium acetate. So this is in part why sodium acetate is able to form a super saturated solution so easily. Same with glucose. Even though there's not an exponential relationship, we can see that it is, or the solubility of sugar is very, very dependent on temperature, which allows both of these materials to form supersaturated solutions fairly easily. Other materials, like salt, we can see barely increases with temperature. Its solubility barely increases with temperature. But it does still subtly increase. There is a positive slope here, even though visually it's kind of hard to tell on this graph just due to the axes. All right, so let's talk about why the temperature dependence of these solids increases with increasing temperature. It all comes down to what happens to the solvent. So as you increase temperature, what ends up happening to the liquid solvent, to our water, is that the molecules are able to move around a little bit more freely. Now, because these molecules gain energy, they're able to whiz through the solution, flow a little bit more easily. What we see is that as a result of this, there is more space between these water molecules. So due to the increasing temperature, there is more space between solvent particles. And as a result of there being more space between your solvent particles, there's more space for the solid solute. So with the increasing number of open spaces, there's more solid that you can actually fit inside of solution. This is why we see the solubility of the solids increase with increasing temperature. However, not all solutions are formed by solids being dissolved in water. Sometimes we dissolve gases inside of water, and in fact, we've already talked about this phenomenon. This is related to Henry's law, which we discussed back in chapter 11. The temperature dependence of this solubility, though, we have not yet discussed. So according to Henry's law, just as a brief reminder, the concentration of your gas, which we are now going to be discussing proportional to its solubility, is generally equal to the constant, known as Henry's constant for that gas, times the partial pressure of the gas. And all other gas laws that we have discussed before pertaining to pressure also apply when it comes to Henry's law. So things like volume, temperature, etc. Now, we would be able to predict, based off of the gas laws, the relationship between pressure and temperature for the gas, but what does the solvent have to do with it? Why does the solubility of the gas decrease with increasing temperature, which is what we can see visually in this graph as well? The solubility on the x-axis now is in units of millimolar, which is 1/1000th of a mole per liter. And this solubility, again, is proportional to temperature on the x-axis. And we can see that the gases illustrated here, methane, oxygen, carbon monoxide, and helium, all decrease in solubility as a function of temperature, right? So we increase the temperature, we decrease the concentration of the gas inside of the solvent. The reason why this happens is for the exact same reason that the solubility of the solids increase, which is kind of awesome. Like, the same rationale can be used to understand why solids become more soluble and gases become less soluble. With your increasing temperature, again, all of your little water molecules are going to be spreading out. There's going to be more open space inside of the solvent. In the solids case, this open space allowed for more solute to fit inside of the solution. And the reason why solubility increased, though, was not just because there's more space, but because the space was being filled with a solid. Solids that sink, solids that are stable. Gases are very different because a gas particle inside of this increasingly open space, also being impacted by the increasing temperature, will have more energy as well. And so a gas pinging around inside of this open area is going to gather the energy it needs to break through and escape. So whereas the increasing amount of space was stabilizing for solid solutes, it is actually destabilizing for gaseous solutes. And we can think of this in terms of, like, let's say, for instance, boiling a carbonated beverage. If you heat up a carbonated beverage, it's going to go flat faster. And the reason it goes flat faster is because all of the gas inside of the solution is also gaining energy proportional to the increase in temperature and is going to escape the liquid much more easily. So thus far today, we have redefined solution. We have discussed how the solutions molecularly can be visualized. We've talked about enthalpy, of which we can use that enthalpy to calculate any amount of heat that we need to, in much the same way as any other Q is equal to N delta H equation that we have worked with can be used. And last but not least, we revisited the notion of solubility. So the amount of stuff that can fit inside of your solution is going to give you a measure of concentration, which we'll talk about a little bit later, but rather Today we discussed what it really means to be soluble and how saturated a solution can get. All right, where we are going with all of this again though is to discuss some of the unique properties of solutions in contrast to that of the pure solvent, so be looking forward to that. In the meantime, here are some molecular view of solutions conceptual problems for you to look at. If you have any questions though on today's material, please do not hesitate to either send me an email if you're in my class or leave a comment down below. If you have any homework, please double check and do your homework. And until next time, class is dismissed.